Hello everyone, my name is Aakash and I'm a PhD student of computer science at Penn State. Today I'll be giving a talk on cache, which is a credit-aware scheduling for public cloud platforms. I hope you enjoy my talk. Tenants essentially use the public cloud to process their data. They are helped by data processing frameworks such as Hadoop, Spark, and Tez. They are also helped by large-scale distributed SQL query engines like Hive and Presto to process their data. Apart from this, there are SaaS-based solutions available like Amazon EMR or Elastic MapReduce, using which tenants can spawn a data processing cluster within minutes and start processing. These frameworks essentially run on the hardware resources of the public cloud. Now, resources in the public cloud can be roughly distinguished as compute, storage, and network. AWS M series, Azure B series are some of the examples of compute nodes that you can provision on the public cloud. AWS EBS is a block-based store that you can provision on AWS, and Azure Blob is an object-based store that you can provision. Network is also varied among various public cloud providers. One of the key indicators of differentiation is the service rate that these various hardware resources offer. Let's look at what is a service rate. The service rate can be informally defined as the speed of a hardware resource. Some examples of service rate can be the speed of a CPU core, IOPS in SSD, or bandwidth of a network link. The service rate can be defined with various units. The public cloud actually offers variable service rate. So providers like AWS, Azure, Google Cloud offer what is something known as a burstable resource. A burstable resource is a resource which has a variable service rate. So let's look at what are burstable resources. Burstable hardware resources can also be classified as CPU, storage, and network. Public cloud providers like Azure, AWS offer burstable CPUs such as T3, Azure B series, Google E2 series, etc. AWS Elastic Block Storage and Azure Premium SSD are also burstable storage options. AWS network has always been burstable. So what does burstability actually mean? In the public cloud, every hardware resource which is burstable offers at least a baseline service rate. In other words, no matter what, this hardware resource which is burstable will offer a minimum service rate which is the baseline rate. But tenants may choose to use a service rate lower than what is their baseline service rate. For example, a given workload may use less than 40% CPU, they may use 20% CPU. In this case, what happens is that the public cloud offers them free credits in return. These credits can later be used to burst above or increase the service rate beyond the baseline service rate up to the maximum allowed. For example, CPU can never go beyond 100%. This is very similar to a token bucket mechanism, which is a popular algorithm in the network side. And hence, because public cloud tenants use a token bucket sort of a deterministic algorithm, the variability in service rate or variable burstable service rate is actually deterministic in nature. Let's take a specific example of a burstable CPU. On your right side here, you can see a token bucket CPU as an example. Tokens or CPU credits are earned at a constant rate determined by the instance size. The instance size baseline service rate, you can see it here, 5%, 10%, or whatever, is actually based on the size of the instance. So a baseline service rate, which is like 20%, would guarantee the tenant at least a 20% CPU availability at all times. Whenever the tenants do not use their CPU, let's say they'll use less than the baseline service rate, tokens get accumulated in this bucket. This tokens can later be used to burst above this baseline service rate up to 100%. Let's take another example, which is AWS EBS solid state drives. Now here on the right hand side, you see a burst credit mechanism or burst bucket rather. Um, Here Amazon offers 3 IOPS per GB or 3 credits per GB of provision solid state drive. So a solid state drive which has 100 GB would be earning 300 IOPS per second. Credits arrive in this bucket, and tenants can use 300 IOPS per second to continuously drive their IO requirement. In case they don't use 300 IO per second, they can burst above 300 IOPS up to 3000 IOPS by using the burst credits accumulated in this bucket. In this table, you can see that in case the bucket is full, which is 5.4 million credits, a single GB would take 1800 seconds to get completely exhausted. But it will take 54,000 seconds for to completely fill up the bucket while using no IO. Similar to SSD, this is an example of hard disk drive. The mechanism is similar to SSD, and the service rate or the baseline service rate is linked to the amount of storage you provision in the public cloud. More the storage you provision, the more is the baseline rate, and more is the burst throughput that you can achieve, which varies from 31 megabyte per second to 500 megabyte per second. Current state-of-art cluster managers such as Hadoop, Yarn, Mesos, Kubernetes lack this understanding of burstability in public cloud. They consider all resources to offer a fixed service rate and make scheduling decisions based on this understanding. This is because they were essentially designed for private clouds. Hence, there is a need to bring cognizance to cluster managers so that they can make better scheduling decisions. Let's look at the pattern of CPU utilization in compute clusters. Recently released Alibaba trace shows us that the CPU utilization remained below 40% up for about 60% of the machines. Older trace like Taboola Hadoop cluster also shows CPU utilization to be below 40%. Even the Google trace analysis show that the CPU utilization doesn't exceed 60%, but where the trace for comprise of a mixture of long-running services, MapReduce, and HPC. Both long-running services and HPC are known to have a high CPU utilization. Hence, it is safe to understand that MapReduce kind of workloads would be driving lower CPU utilization. We did our own analysis of MapReduce workload CPU utilization on Amazon Elastic MapReduce. We use Intel High Bench with PageRank, K-means, and SQL aggregation as our workloads. What we see here is that CPU utilization fluctuates, and as you can see from the left-hand side CDF, is that the CPU utilization remain below 40% for maximum amount of time. On the right hand side, we actually plot a timeline of CPU utilization, and we see here that the CPU utilization fluctuates a lot. However, a tenant will not be able to provision a node with smaller CPU capacity because of peak in CPU utilization as shown in the figure on the right. A tenant provisioning lower capacity node would incur SLO violations because workloads needing high CPU utilization during certain peak point in time will not be able to deliver. So, however, there are lower peaks in CPU utilization, such as the ones shown on the right, when CPU is underutilized and can be used to accumulate burst credits. Hence, there is a need to use burstable CPU based instances for driving low CPU utilizing workloads like MapReduce or any workload which actually have an average CPU utilization which is low but has a pattern of using peak CPU utilization followed by lower CPU utilization. Let's talk about storage based burstable resources. We know that all elastic block storage in Amazon is already burstable. Hence, tenants who choose to use block-based storage for their services do not have a choice of not using burstable resources. We also know that analysis done on TPC-DS workload showed very high IO utilization of up to 100% on HDFS. Hence, not using burst credits for storage is actually a lost optimization opportunity. Tenants can use burst credits to accelerate their workloads and reduce job completion time. We also did an analysis of running yarn over burstable resources using only two nodes. On the left-hand side, you see a timeline of CPU credit balance of the two nodes. At time 15 here, you see that the CPU credit balance has become zero. CPU bound tasks running on this node at the time 15 would be throttled to baseline rate. However, you see that there is surplus CPU credit balance at time 15 on the other node. CPU bound tasks could have been provisioned at this node, but Yarn did not know how to do it. This is because Yarn essentially chooses node for scheduling randomly. On the right hand side, you see a SSD based IO credit balance of the two nodes. Here, there is no slowdown because the burst balance was sufficient. However, considering that the burst balance does become zero for the node here, we see that the IO bound task would have been slowed down while there was surplus IO based credits available. This is an artifact of yarn based random scheduling. Hence, yarn is unable to utilize burst credit balance uniformly across its nodes. In this slide, we try to demonstrate the worst case scheduler behavior. In the task queue, there are tasks here which need IO based burst credits and CPU burst credits. You see the schedule thread can provision this IO based task on a node without any burst credit balance here, and CPU credit requiring task on a node without any burst credit balance, while other tasks which require no credits might be scheduled on nodes which have CPU based burst credits or IO based burst credits over here. Cache fixes this problem. We propose a scheme consisting of two techniques. The first technique is task annotation from the framework. In this case, tasks are annotated as being intensive to a particular resource such as CPU or storage, etc. This annotation is automated through the framework and the user do not have to manually annotate the task. This is followed by burst credit aware scheduling. In this case, nodes of the scheduler are sorted based on the burst credit balance. Burst needing tasks are then allocated on nodes or VMs on descending order of the burst credit balance. Let's dive deeper into these techniques. Task annotation. Task annotations happen in the framework based on the characteristics of the vertex a task is associated with in the tag. A vertex of a tag is synonym to a stage in a Spark. Now, entry level vertices of a DAC, which are also called root vertices, are essentially compute or IO heavy. Similarly, shuffle vertices, which shuffle a lot of data, are essentially network heavy. So using these kind of characteristics, the framework can learn a lot and indicate whether these tasks are intensive for a particular hardware resource. Currently, cache supports CPU annotation or storage annotation, but not both. However, it uses CPU and network annotation or storage and network annotation. The user also has an option to override the framework annotation and annotate the vertices by themselves so as to make the annotations more accurate. Let's see two examples of annotated tags. Here we see the root vertices or the vertices here are annotated as storage by the framework. The vertices here are expected to be extremely heavy on IO because they read a lot of input and are expected to spill. Hence, the framework has attached the storage annotation. Similarly, the vertex here is a shuffle vertex and is expected to use a lot of network. Hence, a network annotation has been attached. The user also have an option to attach their own annotation to the vertex. Here, the user feels that both the tokenizer and summation might be CPU intensive and has attached their own annotation, which might be more accurate. Let's talk about our credit-aware scheduling now. We modify the yarn capacity scheduler to make task placement decisions based upon the task annotation as discussed in the previous slide. Now consider this as the yarn capacity scheduler and these as the yarn internal node data structure. We receive per VM burst credit information from publicly available cloud APIs from AWS CloudWatch. These APIs can be used to query the state of any VM in the AWS system. We then use these burst credit information to populate the burst credits in each yarn node data structure and sort it in descending order of CPU or burst credit balance every 1 minute. Yarn allocates tasks to VMs at a short time scale of every few milliseconds. This is handled by a scheduler thread here. And at first, CPU or storage annotated tasks are allocated in a decreasing order of CPU or storage bus credit balance denoted by this data structure list here. Remember that this yarn node data structure list has already been sorted by the node sorting thread. This process is followed by network intensive task allocation, which is actually allocated in an ascending order of bus rate balance. So what happens here is that a network task allocated on a node which is low on CPU or storage bus credits actually ends up acquiring CPU or bus credit balance while a network intensive task is running on it. So this allows the lower burst balance nodes to actually grow in burst balance, and in the next epoch of the sorting thread, they actually move higher up in the sorted list. So this allows a lot of churning between the yarn node data structure. We conduct our experiments for two optimization cases. We first schedule burstable instances based on CPU burst credits, which is followed by scheduling regular instances based on storage burst credits. We report our results of running cache over CPU-based burstable instances in this slide. We run high bench batch workloads using Hadoop. As seen in the slide, cache performs better across all our experiments except for EMR or elastic MapReduce. However, it is almost 25 to 30% more expensive to run workloads on EMR compared to Amazon burstable instances. Hence, cache delivers the best cost savings across all our experiments. On the left-hand side, we report the CPU utilization of our cluster across the experiments. Cache reports the best CPU utilization across all the experiments. On the right-hand side, we report the standard deviation of CPU credit balance across the nodes in the cluster. Again, cache shows the least standard deviation across CPU credit balance in the nodes of the cluster. This indicates that cache utilizes the most amount of CPU credits across the nodes in the cluster. In this slide, we report our results of running cache over regular instances with storage-based burst credits. We run TPC-DS streaming queries over high-bench tests. We run three experiments, one with 2 VMs, second with 10 VMs, and the third with 20 VMs. Each VM is attached to one SSD only. In the 2 VM case, we see cache is able to accelerate by at most 4.8%, which is less. But this is because cache is able to optimize by for only 2 VMs, which is very little. With the 10 VM case, cache improves the query latency time by almost 20%, which is good. This is further improved to 40% when we have 20 VMs in the cluster. With more number of VMs, cache gets more opportunity for optimization. So we fathom that with more number of VMs beyond 20 VMs, we will be able to see better improvement time than what we have seen in this experiment. We report end-to-end job completion time here in the last slide, and we see that we can have a maximum improvement of 22% of end-to-end time, which leads to public cloud cost savings of equal amount. On the left-hand side here, we show that cluster running cache has a much higher average IOPS. This is because cache is able to utilize storage burst credit balance better and deliver better IOPS to the workloads that it's running. On the right-hand side, we show the standard deviation of burst credit balance across the nodes in the cluster, and we see that cache is able to do a better job in lowering the standard deviation of burst credit balance in the nodes in the cluster. Cache is also able to improve the IO throughput and CPU utilization of the nodes in the cluster, as seen on the slide here. To conclude, we propose cache, which is a novel scheduler for cluster VMs of a public cloud. Cache relies upon the knowledge of burst credit states of burstable resources of the VM and the estimated burst resource needs of the task, which is indicated through task annotations. Low CPU intensive batch workloads, which run on T3 burstable instances, were found to be more cost effective compared to running on Elastic MapReduce and StockYarn. And cache is able to accelerate streaming Hive queries by up to almost 40%. This leads to a direct public cloud savings of up to 22%. Thank you, and I hope you enjoyed this presentation.